Hello everyone! So happy to see you guys staying safe and healthy. I won't waste much of your time, so let's get it started.
Our project is Solar Street Lights, sponsored by Larry Gettleman and the South 4th Street Association. If you guys don't remember us, we are Team 12 or Leo Solar. My name is Nguyen. I'm the project manager. Along this video, you get to meet Harrison Swayne, the electrical engineer, Maxwell Jones, the design engineer, and Hillwig, the electrical researcher. I'll give you guys a quick recap about this project. In 1996, LG&E installed all 75 of these lampposts along South 4th Street with underground wires and powered by a meter drop. Then, the South 4th Street Association decided to purchase all 75 of these lights for their neighborhood. Fast forward 24 years, due to creeping roots underneath that has disrupted the unprotected underground wirings that caused a lot of problem for the association. That's why Larry Gettleman and the South 4th Street Association have sponsored for this Capstone project. We were given these requirements for the system. It has to be fully solar powered. Moreover, it has to be a retrofit and it should not have any connectivity to the mains power. The battery has to power the bulb for at least 14 hours. As of the light source, it has to be LED and it has to be controlled by a low voltage photo switch. As of the light distribution, it has to have a half hemisphere pointing downward, which means it's create a 180-degree arch. A secondary requirement that we have to take in consideration was a controllable brightness feature. To talk in depth about this system, I will hand it to Harrison Swayne.
Thanks, Lee. This is Harrison Swayne, and I will talk about what our group has done since the midterm presentation. Before spring break, our team had the components and the plan to begin constructing our first prototype. With our battery and charge controller chosen, we calculated that our solar array needed to be set up in the displayed configuration. This combination of series and parallel balanced the voltage needs of the charge controller with the current needed to charge the battery. We also discussed adding a clear wall to extend the height of our globe, giving us more internal space for our solar array to lay flat at 33 degrees. Our group also traveled to different Louisville companies to gather information on globe suppliers and lower wattage light sources. Once quarantine started and the labs closed, our team lacked the tools to adequately construct our planned prototype. Luckily, our sponsor, Larry Gettleman, offered to help us by using his home workshop to construct a prototype himself. Using styrofoam, the solar cells were secured in place and wires were fed through the styrofoam for us to connect. The other components were mechanically connected to a metal plate, and copper tubing was used to support the light sources. Once Mr. Gettleman finished construction, he handed the prototype off to Max for testing. Once testing began, the solar array did not output the current that we expected. Under ideal conditions, we expected around 600 milliamps output. When tested on a clear sunny day, the solar array only supplied about 120 milliamps, 70 milliamps of which were actually delivered to the battery. We have theories as to how the modules may be damaged, but we have no extra solar modules to compare against. Overall, the system is functional but does not meet the operational requirements of the design. The other components of our design operated mostly as expected. The battery receives charge well, but is under the needed capacity. The charge controller supplies charge, albeit with a higher power loss than advertised, and the photo switch does detect low light conditions. I'm now going to pass things to Max, who will talk in depth about system testing.
Thanks, Harrison. This is Maxwell Jones, and I'm going to talk to you about the testing procedures for our system. The system can be broken down into 6 main parts that needed testing: the solar array, or cells, the charge controller, the battery, the photo switch, the LED light bulb, and whether or not the system was a true retrofit installation for the globe tops. First off, the solar array had an expected output of 615 milliamps in the configuration that we used. The measured output was 120 milliamps. To try to troubleshoot this discrepancy, we measured each individual solar cell. They're rated for a short circuit current of 218 milliamps, but we only could measure a short circuit current of 0.07 milliamps. The solar modules could have been damaged sometime between when they received and when they were tested. Therefore, they cannot deliver enough current to the battery and failed the test. The charge controller, which regulates the battery's charge and discharge, has LED indicators that do work as specified by the product page, which is great. But the current supplied from the solar array was never sufficient enough to charge the battery, so the full operation of the charge controller could not be verified. The battery was tested by connecting it to the charge controller with the LED light load attached only. The required battery life for this system is 14 hours, whereas the actual battery life was 6 hours, so the battery is not large enough for this system. The LED light bulbs, which are rated for 500 lumens, while we have a constraint of 250 to 1,000 lumens, worked pretty well. They could also be powered by the battery, so they're good for this system. The photo switch, which cuts off current through the load when the sensor detects light, worked exactly as expected. The light comes on during dark conditions. As for whether or not this is a true retrofit installation, we did rapidly prototype the system out of styrofoam with the concept to maximize the spread of solar cells. However, it will need to be modified to fit conveniently into any other of the lamppost globe tops. It's not really a practical retrofit that could be repeatedly manufactured for the about 75 lampposts that are on 4th Street. The base that supports the electronics does block light from emitting from the top of the globe, which was one of the desired requirements. However, since this is not a true retrofit installation, it doesn't really pass this test. Now, I'm going to pass things off to Sean next.
Thank you, Max. I'm Sean Hillwig, and I will be speaking in regards to potential future improvements to our design. To start things off, an adjustable brightness controller could be added to our design, making each lamp capable of having a unique brightness. The adjustable brightness controller was a secondary requirement to the system that, due to the unfortunate pandemic, we were not able to achieve over the course of this semester. The next potential improvement is a higher efficiency solar array. This could be done by reconfiguring the current solar array panels into a more optimal pattern done through testing, or different photocells could be used. With the limited time we've had to build and test the prototype, we've only been able to use one set of photocells. The last potential improvement we recommend is a more secure base connection of our retrofit prototype to the lamp globe top. Currently, the system is utilizing gravity and friction to hold the retrofit in place inside the lamppost top. A potential improvement would be adding screws, clips, or another method to hold the fixture together. And with that, I'll hand things back over to Lee.
Thanks, guys. Now that I hope you guys understand a little bit more about our prototype and how it works, I would like to thank Larry. Without him, we don't even have the prototype that we showed you today. One more person would like to thank is Dr. Faul. Thank you for your guidance in this semester. And last but not least, to everyone in class of 2020. We did it. Thank you.